All right. So since our main goal is to produce forecast, okay, so it is important for you to know how to evaluate forecast accuracy. So there are a number of standard statistical measures that we can use to evaluate forecast accuracy. So it can be done in sample as well as out of sample. So we can use the same standard statistical measure for in sample as well as out of sample to in order to measure the accuracy, forecast accuracy. So we also can use ACF, auto correlation function, the one I mentioned before. So in the previous slide, this one, we use ACF in order to analyze a relationship between current and the past values of the same series. But you also can use the same ACF in order to analyze the relationship between current and past values of the error. So so that one I will explain the ACF of forecast error is actually alternative to what we call that alternative way for diagnostic checking for the model. And then we also can use prediction interval in order to provide what we call that in addition to the point forecast, we also can produce the what we call the values for prediction intervals. Okay, so accuracy is treated as an overriding criterion for selecting a forecasting model. So accuracy represents goodness of fits of the model and how well the forecasting model is able to reproduce the data. So if YT is the actual observation of a time series and FT is the forecast for the same period, then the error is defined as the difference between actual minus the forecast values. Actual minus forecast represent the forecast error. So ET, we use ET to represent a forecast error. So YT are actual value, FT is the forecast values. So usually FT is calculated using data Y1, Y2 up to YT minus 1, and then we produce forecast for the next one. So we use information from Y1 to the first data we have up to the last data we have, and then we produce forecast for the next one. So it is a one step ahead of the last observation used in the calculation. Hence, ET is described as one step ahead forecast error. Okay, so for example, this one, let's say we have the data YT, and then we have data Y1, and then we can do we can use this value to put a forecast for the next one. Okay, and then when we have new observation Y2, and then we use data from the first observation up to the YT minus 1 to produce forecast for the values for time t, for time t, so the next one. Okay, so that, and then for each other forecast you can produce, you can compute forecast error. So the YT minus, so the Y minus forecast values, the actual value minus forecast value gives us the forecast error. All right, so there are three standard statistical measures that we can use: the mean error, mean absolute error, as well as mean square error. For the case of mean error, so we just take average of all errors. So we just sum all the error, take sum of all errors, and then we divide by sample size, so you get mean error. Okay, so however, this one, the problem with mean error is that the positive error can cancel out negative error. So let's say the first error, the first one, the first forecast, and then you compute the error, it is -2, and then for the second one, it is +2 at the size of error, so that when you compute average, it is equal to 0. So ME equal to 0 is just like there is no error. Okay, but there are errors, because the first one -2, the second one is +2, but because of the positive cancel out the negative value, so that it is equal to 0. So it just like that there is no error, but there is there are errors. Okay, because of the positive cancel out negative. So in this case, that's the what we call a disadvantage. Disadvantage of using mean error. So to overcome that problem, we can use mean absolute error or mean square error. For the mean absolute error, each of the error we transform to be positive first. Okay, we use absolute values. Okay, we apply absolute value for each of the error, and then so that negative become positive, and then you compute average, so that we call it mean absolute error. So alternatively, we can also use mean square error. Mean square error. So each of error we square. Okay, we square. Let's say -2 is become a -2 square, so it is equal to 4. Okay, so they're all positive. Okay, and then we take average. Okay, so this one is mean square error. So again, mean absolute error and mean square error is alternative. Okay, it's a solution to avoid positive cancel out negative values in the while we compute the average. We compute the average of the error. So each of these statistics deals with measure of accuracy whose size depend on the scale of the data. They do not facilitate comparison across different time intervals and for different time series. For example, an error of 10 megaliter when forecasting monthly beer production is quite different from an error of 10 megaliter when forecasting annual beer production. Let's say in this case, there are different situations. So the first one, we produce forecast for a monthly data. So let's say for January, the actual value equal to 100, but we produce forecast equal to 90, so that the error is equal to 10. The error equal to 10. Okay, so let's say if let's say we produce forecast for annual data, let's say for that particular year, the value of production equal to the actual value of production for that year is equal to 1,000. But the error we produce forecast it is equal, our forecast is 990. So again, the error equal to 10. So for the two cases, the size of error is exactly the same 10, but for if you consider two cases, so when produce forecast for monthly data, so the size of error in terms of percent, it is 10%. Because the actual value is 10, 100. So the size of error is equal to 10. 10 out of 100. So it is 10%. The size of error is 10%. Forecast error, the size is 10%. But for the case of another, what we call the cases, for another case, we produce forecast for annual data. So let's say 10, the size of error is 10, but the actual value is 1,000. So it is only 1%. So in this case, although for the two cases, although the size of error is exactly the same, equal to 10, but our forecast accuracy, we see that it is more accurate for the case of annual data, because the size of error is just 1% instead of 10%. Okay, so so to measure comparison such as the above, one need to work with relative or percentage error measures. So so alternative to the three measures that I mentioned before, ME, MSE, MEE, okay, you also can use the percentage error, which is defined by this formula. So percentage error. So it's different between actual minus forecast value divided by the actual value and then times 100. Okay, so it's percent error. So the following two accuracy measures are frequently used: the mean percentage error. So for each of the forecast value, you can compute each percentage error, and then for the what we call the entire forecast value, then you can compute the average, the mean percent error. So you just take the average, sum all of the percent error for all forecasts, and then you divide by how many number of forecasts you produce, and then you divide, you get the mean percentage error. Okay, so this one also has the same problem just like mean error, because positive can cancel out negative values. So that to overcome that problem, you can use the mean absolute percentage error, so that you convert all the negative to be positive first, and then you compute average. So this one we call as mean absolute percent error. So know the MAPE. Okay, say 5% means a great deal more than knowing the MSE, say a certain value 180. Okay, so the MAPE is only meaningful if the scale has a meaningful zero, that is a ratio data. For example, one would not use the MAPE for assessing the accuracy of temperature forecasting, since the common temperature scales have fairly arbitrary 0 point. So it does not really, it's not really what we call that meaningful to compute when the values of the variable is not really, although it's equal to 0, but it does not really what we call that represent the absence of the temperature. It's just the value used to to represent different levels. Okay, it's not a true what we call number. So difficulties with the MBPE and MPE also arise when the time series contains 0, since the percentage error cannot be calculated. So if let's say the true actual value of YT equal to 0, then this is undefined and you cannot compute because divide by 0. So the following table give the last 8 beer production figures and forecast obtained by taking the average of each month over the past 4 years. So this example, so let's say we have what we call the data, and then we use a technique to compute forecast, okay, and then we produce forecast, and then we can compute the accuracy measures. For example, this one, you take the difference between two actual minus forecast value, you get your error. So you compute the average of error, so you get mean error. Okay, so if of the error you convert to be positive, okay, you apply absolute. I mean, you take absolute value of each of these. So all positive become all negative value become positive, and then you take average. So it is a mean, and then you get what we call as a mean absolute error. You can use the mean square error. So you square each of the error, and then you take average. Okay, this is mean square error. For the case of percent error, okay, so to overcome, I mean, to what we call that, based on what we call that explanation given before, okay, so this one you also can compute the percent error. I mean, you take the difference, and then you compute the error, and then you divide by the actual value, and then times 100 you get this. You take average, you get the mean percent error. Okay, but again, to overcome the problems of positive cancel out negative values, you can compute the absolute percent error first, okay, and then compute the mean absolute percent error. So if let's say you are comparing two different models, okay, so this for one model, and then you have another model, and then you also can compute the same accuracy measures. So for the case of mean error and then mean percent error, I mean, in order to say to determine which model is better to produce better forecast, so we select the model that produce the value of ME and MAPE that closer to 0. Okay, which one is what we call that closer to 0? If you have two models, so let's say one model is let's say we compute MPE. So this one negative 3.25. So we have another model that produce MPE equal to negative 4. So which one better? So you need to choose the one that's closest to 0. So meaning that this one negative 3.25. Although negative 4 is smaller than this. Okay, but we want, because I mean, we want our forecast to be accurate, so that in that case we want our error to be as small as possible, so that we want it to be close to 0. Okay, the accuracy measures. But for the other accuracy measures, okay, MAE, MSE, and MAPE, you can simply say that we want it to be as small as possible, because it's impossible to be negative. It cannot be negative. Okay, so that I mean, we can simply say that we will select a model that has the smallest value of MAE, MSE, or MAPE. But you cannot say the same for the case of ME and MPE, because it can be negative, so that negative 4 and negative 3.25, negative 4 is smaller than this. Okay, but we will select this one because it is more, it is closer to 0. All right, out of sample accuracy measures, the summary statistics so far considered measure a goodness of fit of the model to historical data. Such fitting does not necessarily imply good forecasting. Okay, because normally when we what we call that, when we estimate model, the computer, for example, or the technique that we use for estimation, we find a set of values for parameters, estimated parameters, that give us the smallest value of error. It will force the error to be small. Okay, when estimate the parameters, so that so normally what we call that, the model perform quite well when we estimate for in sample data. So in order to know whether our model is really able to produce good forecast for the future outsample future values, so that so in order to measure true outsample accuracy, the total data are divided into an initialization set and a test set, or whole out set. So we divide data. You have a set of data sample. Okay, so a better practice is that you split data into two. Okay, and then use the first set of data to estimate for estimation. Okay, because we know that when we estimate, normally it will perform quite well in sample, because the technique that we use to estimate, it will find the value of estimate that give us the smallest possible value of error. Okay, so in order to know, again, in order to know whether is the model that we use is really able to produce good forecast for our sample, then we split data into two, and then use the first set of data to estimate for estimation, to estimate parameters, and then after we estimate, produce forecast, and then after produce forecast, we compare the forecast value to the data that the second set of data that we keep in order to evaluate forecast accuracy for our sample. Okay. So the initialization set is used to estimate any parameters, and to initialize the method, forecasts are made for the test set. Test set, our sample, the data that the set of data that we keep to evaluate the outsample forecast. So since the test set was not used in the model fitting, these forecasts are genuine made without using the values of the observation of the time series. The accuracy measures are computed for the test set only. Okay, so in this case, you can compute the accuracy measure that the one that we discussed before, the MPE, MEPE for in sample evaluation. But you can also use the same what we call that statistical measure for our sample, to compute for our sample. But we split lah. You do not compute using errors for in sample and out sample together. You compute it separately for errors, forecast error in sample, and then you compute for our sample only using the errors for our sample only, forecast error for our sample only. Again. And then ACF or forecast error, the ACF or the one step forecast error are very useful in determining if there is any remaining pattern in the errors or residuals after forecasting method has been applied. It is not a measure of forecasting accuracy, but give an indication if the forecasting method can be approved. Okay, so remember that the error term for most of the model, it must be something what we call the random values, and there is not most of the model requires that the errors should not be auto-correlated each other. You remember, for those that already learned applied econometry, so after you estimate the model, you need to perform diagnostic checking on the model. I mean, you need to check the residuals, because residual is the estimate for the error term of the model. Okay, so you need to make sure that there is no relationship between current error and the previous error. For example, current error or other values of the error. So you need to make sure that there is no auto-correlation problem. So if you use econometric model or regression model, you can use Debye-Watson. Okay, for example, the Debye-Watson test to test for the first order autocorrelation. But if you have time series model, okay, time series model or technique forecasting model, and then you also can use the ACF, ACS alternative of what we call that, in order to know whether there is a relationship between current error and the previous errors. Okay, so if current and just the previous one, the first order, then it is equivalent to the Debye-Watson test. Okay, Debye-Watson. But ACF also allow us to evaluate if there is higher order of autocorrelation, because you remember just now I explained to you that the autocorrelation, if you go back to, okay, the one that given here, but this one, for this example, we use autocorrelation to assess correlation between current and past, the previous value of the same series. Okay, you also can produce the same ACF, autocorrelation function, and you use it to not to the actual observed values, but you applied it on the residuals, residual produced by the model, so that in order to know whether there is autocorrelation between current values of the error and the past values of the error. Okay, so if the forecast error appears to be a random series, then the ACF would reflect that with almost no significant autocorrelation. So meaning that it will, if you produce ACF for the residual on the, on the residual to inspect the relationship between current and the previous residuals, we need all the values of autocorrelation to be inside the critical values, the interval. Okay, the two standard error bands. All right. So if not, then we need that there is a correlation between what we call that autocorrelation problem. I mean, there's correlation between current error and the past errors. So so if there is some sort of pattern in the ACF of error, it would imply that the forecast method could be improved. So you refer to the example that we considered just now. It is clear that some of the autocorrelation for errors would be significant. Some sort of it's possible that some sort of seasonal pattern present in the correlogram. So if you look at to this one, so you produce the ACF. It's possible that it seems that there will be a high autocorrelation between the current error and current error, the error at lag 3, at lag 3, because you see that for so let's say this you can see this one -12 quite large, and then after 3 values and then high value, and then after 3 1 2 3 the next 3 and then high value. So maybe you produce ACF, then it may be possible that at lag 3 at lag 3 it will have high what we call that values of the autocorrelation, so that the model has the problems of autocorrelation. Okay. So I mentioned just now, so the Binge-Watson test you used before in applied econometry, that one only for to assess relationship between current and previous one, the first order autocorrelation. So this one you use ACF, then you can what we call that assess for higher order. So this one at lag 2, meaning that for second order, the third order for lag 3 and so on, between YT minus 3 and so on. Okay, not only between YT, not only between at time t and t minus 1, but also what we call that between t and t minus 2, t and t minus 3, and so on. And then prediction interval as well as forecast value, it is also desirable to provide accompanying statement, usually in the form of prediction intervals. It is useful because it provides the forecaster with the worst or best case estimate, and it is a sense of how dependable the forecast is. Forecast cannot be expected to be perfect, and the prediction interval, what we call that, okay, so sense of how dependable, sorry, this one, forecast cannot be expected to be perfect, and the prediction interval emphasize this. So prediction interval are usually based on the mean squared error because it provides an estimate of one step forecast error. All right, so the usual assumption for constructing prediction interval is that the forecast errors are normally distributed with zero mean. So under this assumption, an approximate prediction interval for the next observation is given by this formula, the point forecast. Okay, the point forecast plus minus a critical value that you can get from a standard normal table, and then square root of the MSE. So this one, the Z determine the width of the prediction interval. So you want to compute 95% prediction interval, then you use this one, the value of this is 1.96. Okay, point forecast plus minus 1.96 times the square root of mean squared error, that will give you an approximate prediction interval for 95% prediction interval. But this one just approximate value. So later on in the following topics that we will use what we call that more accurate what we call that calculation to compute what we call that the forecast interval.